safety think the ferrets are Dr.
I don't get on them.
They're not.
No, I grew up in a small town that had a big fair every year, and when the people came in that ran the fair, you could just they were not the most aware of their surroundings after a day of working. I don't know if you know what I mean.
Yeah.
They had a few substances, both legal and illegal, I think. And it was, yeah, I would not trust them putting together fair equipment. I like my rides like permanent structures,
Yeah.
built by engineers.
A couple missing screws and bolts.
Yeah, right?
Nothing too serious.
No.
Just life threatening.
I only go with people who will make me get on the ride.
Oh yeah.
That's relevant. If I'm not being peer pressured, I'm not going.
Yeah, I love it. They made me go my senior year of high school, and I had just dislocated my knee, couldn't barely walk. Number one, and they were trying to get me on a wheelchair. They had a wheelchair. Then we could have, fun. I was like, I don't trust you. I don't trust you to push me around in a wheelchair.
This forgets. Guys. Did you have crutches?
I wasn't on crutches at the time. I didn't go to hospital.
Oh, so you just vibing. That's crazy.
Am I recording? I think I'm recording, right?
Yeah, you're fine.
I gotta upload the last one. There he is. Getting worried about you. Okay. All right. So we little review for fun. Funsies. Is that a thing? Specific heat. We talked about specific heat, right? What do we know about specific heat? Because that was. Oh, was that last week?
Yeah.
It was Friday, right? That's why everybody forgets. In the weekend. Specific heat. What do we know? Who's gonna give me a formula? Units.
Specific.
Come on now.
Q equals MC delta T.
Q equals MC delta T. Right on. Let's pull up the white screen. Q equals MC delta T. And what are the units? C is the unit. C is specific heat. What are the units?
Joules per kilogram Celsius.
Okay. Anybody remember the chemistry units? Matthew? Just dropped it on you. No?
No.
You know?
No.
Isn't it calories? No, right?
Yeah, it's calories per gram
Resources.
degree Celsius.
Is that little calories or big calories?
That's little calories. Good question. Not kilocalories or food calories.
You're gonna have to explain that. Low calories, big calories.
So, okay, side note for Matthew. 1 capital C calorie is 1,000 calories, or 1 kilocalorie. Little c.
Why did they have just use a different word?
I don't know why
Why
they.
is it just a capital C?
I don't know.
Misleading.
It's chemistry. They do things weird.
Misleading.
But at least they have something nice because the specific heat of water is 1 in those units, right? So the specific heat of water is 1 calorie per gram degree Celsius, or 4186 joules per kilogram degree Celsius. So these are the metric SI units. These are the chemistry units. They're both handy. Okay, so what's going on? If I have, let's say, a solid, right? I'm drawing. Remember, we represent a solid by molecular bonds as springs, right? And we heat it up. What happens to the molecules? They vibrate bigger and bigger, right? It expands, it warms up, right? Okay, let's see what happens when I warm it a lot. I got a little simulator I want to pull up. So I'm going to raise it. Everybody got what they want off this? Okay, let's fire this up. Alright. Okay, here we have 2 hot plates. One hot plate containing 50 grams of water in a container, the other hot plate containing 50 grams of ethanol in a container. And now I'm going to heat these are liquids, and I'm going to heat them. What's going to happen? The molecules are going to move faster, the temperature is going to rise. Right? But at some point, something interesting happens. All right, you can see the temperature rising over here, right? For each one, it's going up. Some molecules are escaping because they're moving rather fast. All right? And then notice what's happening here to the ethanol right now. What happened to this curve?
It's flat.
Flat. Why is that? What is the ethanol doing at this point? It's going from a liquid to a gas. So it's called, well, boiling, right? Evaporation is like when I lose a couple molecules at a time. But here I'm making all the molecules disappear. And then the water boils, right? So what happens during boiling is I change states of matter. All right, so when I was a liquid, and if we reset it, and run it. So you can see here, right now I got one ethanol molecule escaping. Because some of the molecules, remember, we learned this works for solids, liquid, gases, right? They're not all going the same velocity. Some are going faster, some are going slower, right? We learned that. So some of the molecules are going fast enough to escape, right? But when I get up to the boiling point, that means all the molecules are moving fast enough and it boils away. Right? Does that make sense, everybody? Now, what's my picture of a liquid? Remember, the model we used was, right, things connected by some bonds, but not a lot of bonds, right? So I drew it in pairs. Doesn't have to be pairs, but you get the idea. And then I'm going from this state to a gas state, which is what?
Free moving.
Molecules free. So what happened to all that energy? I'm putting in heat, but the temperature doesn't change, right? The temperature stays the same. What's happening is what? The state of matter is changing. I'm going from bonds to no bonds. So the energy I'm putting in is breaking the bonds. Right? Does that make sense, everybody? So as I put more energy in, I'm breaking more of these bonds. I'm not raising the temperature of the gas because it's already at the melting point or the boiling point. Right, so that's what's going on. We call this latent heat. So here we have specific heat. And then during this flat curve here, we have latent heat. Right? And that's the heat required to change the state of matter. Okay? Does that make sense to everybody? Let's look at the other simulator. I have another simulator on this. Okay. So this one we're going to start with just one substance, ice. So we're going to start with a solid. Alright, and I'm going to melt the solid, so I'm going to put heat in, and let's see what happens. I'm putting heat in, right, there's the Bunsen burner, and what's happening to the temperature? It's warming. And then at 0 degrees Celsius, what happens to the ice? It melts. So I'm going from a bunch of bonds to just a couple bonds. I'm breaking bonds, changing my state of matter. And now, notice it doesn't start to rise again until it all melts. So this is specific heat, this is latent heat, this is what?
Specific.
Specific heat again. Right? Does everybody see that? And then, of course, you'll see some of the water molecules escape because they're moving fast, but most of them don't until we get to 100 degrees Celsius. And then at 100 degrees Celsius, what happens?
Latent heat again.
Latent heat again. Right? And I'm changing states again. I'm going from a liquid to a gas. Okay? Does it make sense to you guys?
Are we stopping at 100 because that's technically like
That's the
transition
boiling point.
point.
Yeah, so that's when you're going to break all the bonds. Right?
So you like, as in like, you don't need to make it any harder than that to.
Right. You get to 100 and then it'll boil away. As long as you keep adding heat, it'll keep boiling until you run out of water, and then it turns into hot steam. All right, so this here is called the latent heat of fusion. and this is the latent heat of vaporization. Right? Makes sense. Fusion, we're talking about solid, liquid boundary, vaporization, right? Liquid, gas boundary.
Dr. Browning.
Yeah.
But I've heard that it's not gonna be the same temperature everywhere on Earth, right?
Oh, right, because of, atmospheric pressure. So this is at sea level, 100 degrees Celsius. When you go up to like a mountaintop, it's less because there's less atmospheric pressure, so it's easier to boil. Anybody got a pressure cooker at home? You may know what I'm talking about?
Yeah.
It actually raises the boiling point because you create pressure, you don't let it escape, so you can get the liquid much higher than 100 degrees Celsius before it boils because you're containing it and adding pressure to it.
I was slow one of the first times that I was messing with one of those things. I didn't realize there was something in there. And then, like, you know how they have, like, the little tab that you lift up and lets all the steam out?
Yeah, it's hot steam, isn't it?
Yeah.
Yeah.
It was not a good day.
Not a good day. Or if you go to a mountaintop, then things boil at a lower temperature. Not much, but a little bit. All right. So, the formula for latent heat. Q equals ml. So L is the latent heat. That's what it's called, the value. It's not a coefficient, it's called latent heat. And we have two latent heats, vaporization and fusion. So you either have a V or an F depending on the boundary. Okay? What are the units for latent heat? Can anybody tell me? Looking at the equation.
Mm,
I need what over here?
joules.
Joules. And I have mass, which is kilograms. Joules per kilogram. Right? Or it could be calories per gram if you use the chemistry units. Okay? Let's look up some values. So I'm gonna pull up a table. Let me erase this. I'll pull up a table of these latent heats. Okay. All right, this is a good table. So here we have various latent heats. You can see we have some gases, we have water, ethyl alcohol, we have solids, right? And you can notice the units. They give us joules per kilogram. So these don't have the calories, these are just joules per kilogram, right? And melting point, boiling point, right? And you can see that. And you see some value. And what do you notice? These numbers are big, right? And particularly look at water. Where's water? It's not the biggest, but it's pretty big. Where is it the biggest?
Yeah.
Cool.
Aluminum's a little bigger, isn't it? Silver's 10 to the 4, so this is 10 to the 5, 10 to the 5. So it's a pretty big number, 3.33 times 10 to the 5th joules per kilogram. So to raise 1 kilogram of water, or to melt 1 kilogram of water takes 3.3 times 10 to the 5 joules. It takes a long time. It takes a lot of energy, right? When you're melting stuff. Does that make sense, everybody? And then you can see, of course, the 2.26 times 10 to the 6. So it's even bigger here for boiling. All right, melting's pretty big, boiling's even very big. Oh, this number's huge, look at that. Aluminum, to boil aluminum, 1.4 times 10 to the 7. So, big numbers. Okay. All right, let's look at a problem involving this stuff. So, I think I got the textbook open here. Let's try a problem. What do you guys say? I think we're in this chapter, are we? Yeah, specific heat. We want to go to latent heat. Okay, let's try number 13. That's one's like plug and chug. Can you guys read that? How much energy is required to change 40 grams of an ice cube from ice at negative 10 degrees Celsius to steam at 100 degrees Celsius? So what are we doing? We have ice, and we're turning it into steam. Let's think about the process. Where does the ice start? What temperature?
Negative 10.
Negative 10. Does it melt at negative 10?
No.
No. So what do I gotta do?
Heat it up.
I gotta heat it up to 0. Then I gotta melt it. And then what do I gotta do?
Heat it up to 110.
I gotta heat it up to 100.
100.
Because what happens at 100?
Vaporize.
It boils. So then I gotta boil it. And then I gotta raise it 10 more degrees to 110. Right? Does that make sense, everybody? So if I look at my formula here, the thing I'm talking about is we have first Q1, that's going to be the warming the ice, plus Q2, which is going to be melting the ice, plus Q3, which is what? Warming the water, plus Q4, what's Q4?
Boil the steam.
Not yet. I'm boiling, I'm creating steam. And then plus Q5, warming the steam. Okay, this is what we gotta calculate, Q total. How much energy, all these cubes, right? Make sense to you guys? Okay, what's the formulas I need? I need 2 formulas. What formulas do I need?
Q equals ML
Q equals ML,
and Q equals MC delta T.
MC delta T, exactly. Okay, but I need some values of these things, right?
Yep.
I know M. What do I need to know? I need to know specific heat and latent heat, right? So latent heat of fusion, we can just look at our table. I think I have it right here, don't I? What's the latent heat of fusion for water? 3.33 times 10 to the 5th joules per kilogram. I need latent heat of vaporization, which is what?
2.26 times 10 to the 6.
10 to the 6 joules per kilogram. Okay, I need the specific heat of ice, specific heat of water, and specific heat of steam. I need all 3, don't I? Let's see if we can get a table of those. Let's look in the textbook. I think they give me tables, don't they? We go back and we look under specific heat. I bet there's a table here. Look at that. Ice. What is it for ice? Ice. 2090 joules per kilogram. And then water, anybody remember water? I think your textbook uses 4186. And then we need steam. Do they give us steam in here? Yep. It's pretty close to ice, isn't it? 210. Okay. So we have everything we need. See if you can solve it. All right, what do you gotta do? You just gotta plug and chug, don't you? Anybody got a calculator with them? Should always bring a calculator to class. You gotta practice physics to know physics, right guys? PPKP. Practice physics, no physics. I'm gonna start using that. We should get t-shirts made. PPKP.
Is the specific heat for the ice to 2090? Or
Yeah, 2090. Yeah, that handwriting. Thank you. And then the steam is 2010. So you got to put in all those numbers. It's just a lot of typing, but right? It's gonna be what? I'll pull up a. Let's see, how much do we
So
have?
for Q1, Dr. Browner, we're just gonna use Q equals MC delta T, right?
Yeah. So M is 40 grams. Oh, what is that in kilograms?
40 times 10 to the 3.
Yeah, 0.04, right? And T initial, T naught is negative 10 degrees Celsius. T final is 110 degrees Celsius, right? Let me pull up my white screen. We can do these together. So Q1 would be the mass of ice, 0.04, times the specific heat of ice, which is 2090, times the temperature change, which would be what?
Negative 10 to 0.
Yeah. So T final is 0, T initial is negative 10, so negative and negative is plus 10, right? That's Q1. Everybody see that? Q2 is the ice melting, so that's going to be 0.04 times the latent heat of ice, which 3.33 times 75. Bless you. Plus now I gotta warm that ice. So it's 0.04 times specific heat of water times 100 minus 0. Because T final is gonna be 100, I'm gonna get to the boiling point. I started at 0, right? Because here I melted the ice. So here I raised it to 0, then I melted, so I'm at 0, I'm gonna go to 100. Now I got that's 1, 2, 3, and I gotta do number 4, which is boiling. So again, it's the mass of ice times the latent heat of vaporization, 2.26 times 10 to the 6. That's a huge number, right? And then we have now steam times the latent specific heat of steam, 2010 times 110 minus 100. But everybody see how I put all that together? Jared, you with me?
Yep.
So put all that in and that should give you the answer. This one's just plug and chug, so you get the idea. We'll do it more interesting one next. You may got an answer yet? Almost, Mary? You got an answer, Jared? What'd you get?
122,104.
122,000?
Yeah.
104?
Yes.
Joules, I assume?
Yes.
They probably rounded, I imagine. 1.22 times 5. Yeah. Okay, let's try a more interesting one. This one's just plug and chug, all right? You didn't have to think much. Let's try one more fun. All right, everybody got this? I can erase this. All right, let's try one a little more interesting. Ugh. I don't like any of these problems. Let's go back. We'll pick one under the latent heat section. I just gotta pick a different one, that's all. Alright, let's try number 15. This one's not too hard. I think it'll be pretty easy. Because it has answers here. Okay, so we have in an insulated vessel, 250 grams of ice at 0 degrees Celsius is added to 600 grams of water at 18 degrees Celsius. What is the final temperature of the system? How much ice remains when the system reaches equilibrium? Okay. Okay, so what's going on? We're taking ice? We're putting it in water. Anybody have ice water this morning? Or did anybody have an iced tea? I had an iced tea this morning. Put ice in the water.
We all
It's
need to drink more water.
freezing outside.
It's freezing. Why are you drinking iced drinks, right? You drink hot tea today.
We all need to drink more water.
Right. So what happens? They come into thermal equilibrium, right? So we want to find that. So let's try this, number 15. We are going to need some numbers like the specific heat of water. You're going to need that number. Latent heat of fusion, you're going to need that number, aren't you? I don't think we're going to need the steam numbers, are we? No, we're not going to get to steam, right? We're nowhere near 100 degrees Celsius. What's the starting point of the ice? What temperature does the ice start at? 0. So we won't need to warm the ice, right? Because we're already at 0. So we do need these two numbers. I'm going to erase what we don't need here. We don't need that. We don't need this. Okay, so we have Q of the ice plus Q of the water equals 0, right? Now the ice could be, it could melt and it could warm, couldn't it? We don't know what's going to quite go down, do we? So we got to do a little test. So normally I like to let a big equation solve everything, but here we got to do a little thinking, a little test beforehand. How much energy would it require to melt all this ice? How can I figure that out? I want to take all this ice and melt it. How much energy would that be?
Latent heat?
Latent heat. So the formula is what?
Q equals ml.
Q equals ml. So M is what? Is M for us? 0.25, right? L is 3.33 times 10 to the 5. So to melt all that, someone can multiply that for me? $83,250 joules, right? That's how much energy it would take to melt all the ice. Now what about the water? If I wanted to be an ice water, what do I need to cool the water down to?
0.
0. So let's see how much heat I would take out of the water if I were to cool it down to 0. Does that make sense, everybody? And compare these two. So this is the melting the ice. Melting all the ice. All right, how about Q of cooling the water? Cooling water to 0 degrees Celsius. So what's that formula? Q equals MC delta T. What's M this time? 0.6, right? Because it's 600 grams. And C is 4186. And what's my temperature change? T final is 0. T initial is 18. Wait a minute. This should be negative, shouldn't it? I put 2 negatives there. I was not being careful. Why did I put 2 negatives? Because it's losing, right? The water's losing heat, so it should be negative. What do we get for our value?
Negative 45209.
Negative what?
45209.
So 45,000, right? 209. So what does this tell you? To melt all the water, or to melt all the ice, it takes 83,000 joules. To get the water down to 0 degrees Celsius is only 45,000 joules. So what does that tell you?
Not all the ice melts.
Not all the ice melts. So now I know how to set up the problem. Because I didn't know if all the ice melted and it warmed, or if it got down to 0 and then not all the ice melted because I didn't have enough energy. So now we know. Final temperature is going to be what for this system? Not all the ice melted, so what's it going to go to? 0. Right? Does that make sense to everybody? My final temperature should be 0. Right? 0 degrees. Because I can see it takes way more energy to melt the ice than it does to cool the water to 0. So that means we're only going to melt part of the ice. So when I set up my formula here, Q ice plus Q water equals 0, I'm going to cool all the water, but only a fraction of the ice is going to melt. Yes?
What if you, well, never mind, I guess it's insulated. I was going to say, like obviously it's not going to stay at 0 degrees forever.
Yeah, because right, we're assuming insulated, so we're not worried about transfer to the environment.
Okay.
We're going to do a heat transfer next week. And we'll see how that plays into things. Yeah, so, all right. So I'm going to set up a formula here, and I'm going to say M unknown. So this is some mass of ice. We don't know how much is going to melt. So M of ice times latent heat of fusion plus mass of water, specific heat of water, times delta T of water equals 0. All right, does that make sense to everybody? And I'm solving for this unknown mass M here. All right, that's what I'm looking for. So rearrange it, bring that to the other side, divide by L. I get M equals minus mass of water, specific heat of water, delta T of water, divided by the latent heat of fusion. So the mass of water is 600 or 0.6. Specific heat of water is 4186. We already did this, but I'm writing it out again. Delta T would be 0 minus 18. That's negative times a negative. That's going to make it positive. I need a positive mass, so that'll work out. Latent heat of fusion is 3.33 times 10 to the 5th. Right, everybody see how I did that? Put in your numbers and we should get an answer.
Why'd you use the ML again instead of MC delta T in the equation on the left?
Because this is the ice melting, so it's latent heat. There's no temperature change, so there's no delta T. And it's only a fraction of the ice. This tells me the ice that melts. So this isn't my answer yet. This is just what? What's the answer?
0.136.
So this is what melts. 0.136. And the question asks what?
How much left?
How much remains? So what do I gotta do?
Subtract.
Subtract. So what remains would be 0.250 minus 0.136. Which is 1. Is it 24? No, what is it? 1 point what?
Or
1.14?
Yeah.
Or 0.1? 114. Right, or 114. If you switch to grams. Which they did. We didn't kilograms, we just switched to grams. Right, so you see how this, so you gotta think of these problems when you're doing them. Right? Does all the ice melt? Does only part of the ice melt? If all the ice melts, what's my new final temperature? So you kind of have to compare different scenarios to see how much heat you have or how much heat you can transfer.
I have a question. Before we did that, I took the joules to melt the ice and then divided it by the joules. Or the joules to freeze the water divided by the joules to melt the ice and multiply by 250, you got the same answer.
Yeah.
So it's basically, is that basically the same thing?
Well, here's what you took this, right?
Yeah. Basically it's the same exact formula.
I mean, yeah. You're right, you did the exact same.
I just didn't multiply them all out because I already saw them.
Yeah, but you did the same thing.
Yeah.
Good job, Jerry.
I guess sometimes I think it's different, but it's the same.
Yeah. No, but it's another way to see it. Alright. I don't have time to do another one, but we could give you to look at one. You guys have access to the book, right? Does everybody have access to the book now?
I think so. Our assignments still aren't in campus.
Okay. I've been taking care of so many other problems. I'll get to that one eventually. They'll get there eventually.
I don't care.
But it's good to remind me.
Speaking of, do you have office hours? Yeah.
Yeah. Where'd my phone go? Oh! Right there. We can look at this.
Yeah, thanks.
We should.
There's one due Friday, or Sunday, sorry.
Should be one new
I
Sunday.
don't think so. I checked yesterday and it seems that the next one's gonna be on the 9th.
That'd be nice.
Check on home, go to home, and then, oh, your home is different. View as a student maybe. Yeah. Oh, you're in syllabus. Go to home though. Why don't you go to
I
home?
keep clicking on.
That's what
taking-
happens when I go on campus. I hit home and then I can go to
Go to modules though. I think modules will work.
Yeah, I guess that's home.
Yeah, there you go. So go to principles of physics. Right
And the
above.
textbook? Oh.
Yeah.
That one?
Yeah, this is how we get into the book. or
Yeah.
Into the assignments,
So I
right?
don't
Yeah.
get into the book like that.
The assignments.
How do you get into the book?
I press like the ebook tab.
Okay, let me go out as a student.
If you go directly to the book, that's
Yeah, I'm just gonna go to the book. So I gotta close the student. New student view. Unassigned. Okay, so class schedule. What's today?
Wednesday, the
Yeah,
23rd.
16 is already gone, right?
Yeah, 16's done.
There you go, you see? That's what I'm talking about.
Whoa!
Yeah. The
What
next one's
happened?
gonna be on the 9th. Like February 9th.
That doesn't make any sense.
Okay, 3 weeks.
Yeah.
No.
It looks a little weird, right?
Yeah, a little weird.
Seventeen, 18, and 19.
Yeah, I didn't-
Maybe you push the 17 to the 4th.
yeah, 17, but it shouldn't probably be due this Sunday. Is this Sunday the 26th?
Yeah.
Okay, whatever it may be. Because you're the physics and calc book and the physics book, they usually line up, but in this chapters they don't. So this material is in their old chapter, and in your book it's in the new chapter. I don't know why they did that. So you shouldn't have homework due this week.
I
But
should?
No, you shouldn't. You could start it though, because we're talking about latent heat, specific heat. But then we're gonna get into first law stuff next week, and that's be the rest of the chapter. So if you look at the chapter that we're in right now, if I can open the book,
So the next homework is gonna be due when? The 26th?
the second.
Oh, the 2nd.
Second. So if we look at the chapter, how do I get to the book?
And
I
we
opened
have.
the ebook. Here, let me show you the text.
Sure. And Dr. Browning, we have our exam on the 12th, right?
Is it the 12th? It might be.
Yeah, I think so. Second week of February.
I'll look. Let's talk about the chapter first though.
Sure.
So we covered 16, right? 16's all done.
We did, yeah, we had a homework
Direct expansion.
due Sunday.
And then 17, if we look at 17, the outline, we did specific heat, latent heat,
Yeah.
And in the other class, that finishes their chapter. So this is all another chapter. So we're gonna move. So we move the homework back because we're gonna do all this next week. So the homework's back an extra week. I wouldn't say wait all till next week.
No.
You can start doing some of the specific heat and latent heat problems.
Nah. Yeah.
And then we're gonna do
Do Monday, do
Then after chapter 17, we are done with thermodynamics, right? Or no?
What's an 18? Because we got 18. 18 is second law of heat engines. Yeah, so we got 2 more chapters, 17 and 18.
Mm-hmm.
Huh, weird. You guys don't have the.
Homework this week.
Oh. Oh, you guys don't have heat transfer.
No, I thought you said it was
Oh, energy. We're gonna do energy transfer Friday. So we're gonna jump down to do chapter 10 Friday, and then we'll hit the stuff in the middle next week.
I won't be here.
You're not gonna be here Friday? Where are you going? You told me, I forgot.
Orlando.
You're gonna go freeze your butt off, and we're gonna laugh at you because you're cold in Orlando. Who's just gonna go ride rides?
All the lines will be empty.
That's true. Because it's gonna be cold. Alright, can you stop the recording for me?
Sure.